let's unpack this. If you asked any theoretical physicist what their ultimate mission is, the answer always seems to point towards the theory of everything, the TOE. And this isn't just like collecting a list of rules. It's about finding that single, coherent, just breathtakingly elegant equation that unifies all matter, all forces, into one big framework.
And it really sounds philosophical, but it's born out of a very real, very deep crisis in physics.
Right.
It's the driving ambition, because we know right now that our understanding of reality is fundamentally broken.
Yeah.
It's incomplete. We have these two incredible breakthroughs in the 20th century, two magnificent ways of describing the universe.
But they don't talk to each other.
They absolutely refuse to. They're architecturally incompatible. They cannot describe the same things at the same time.
And those two pillars are, of course, general relativity and quantum mechanics. So general relativity, Einstein's masterpiece, that's the physics of the very, very large. Yeah.
Exactly. Gravity, planets, galaxies, the expansion of the whole cosmos. It treats space-time itself as this dynamic, warped, flexible fabric. It's all geometry.
And then on the other side, for the very small, you've got quantum mechanics.
Precisely. The subatomic world. And this framework describes quarks, electrons, photons, and it governs the other three fundamental forces.
Electromagnetism and the strong and weak nuclear forces.
Right. And quantum mechanics is, statistically, it's the most accurate and successful scientific theory we have ever devised. But it's language, it's math. It's completely alien to general relativity.
And the crisis hits, the math just collapses when you try to force them in the same room, when you try to quantize gravity.
Exactly. For the other three forces, we have a tool called quantum field theory, or QFT.
Right.
And QFT basically says forces are carried by particles, the photon for electromagnetism. But if you try to apply that same logic to gravity, you invent a particle for gravity, the graviton. The math just produces immediate, unmanageable chaos.
I've heard them called unmanageable infinities. And that's not just like a rounding error you can get rid of, is it?
Oh, no. It signals a total breakdown of the theory itself. In the QFT math for gravity, when you look at how these hypothetical graviton particles would interact at tiny distances, the equations for energy don't just give you a big number, they give you infinity.
A literal infinity.
A literal infinity, and no amount of the usual mathematical tricks we use to, tame infinities and other quantum calculations.
Yeah.
None of it works here. It just shows that the structure of general relativity, when you push it down to the quantum level, is completely unstable.
And this breakdown happens at a very specific, very crucial point.
It happens at the Planck scale. This is a scale that's it's almost impossible to imagine. It's about 10 to the minus 35 meters.
Wow.
And it defines this energy regime where gravity, the theory of the large, and quantum mechanics, the theory of the small, they have to meet. They become equally important.
Like in the first tiny fraction of a second after the Big Bang, or inside a black hole.
Exactly. Our normal ideas of space and time, they just dissolve at that scale.
So this is where string theory comes in. It's not trying to patch up the old system, it's saying the very foundation we've been using is just wrong.
It is the ultimate top-down revolution.
Yeah.
Other attempts, they try to start with general relativity and work their way down, a bottom-up approach.
String theory does the opposite.
It does the opposite.
Yeah,
It starts with a completely new idea about what the universe is made of, and then hopes that all the physics we know, general relativity, quantum mechanics, all of it, will just naturally fall out as consequences of that initial idea.
That's a huge gamble. You're changing the most fundamental piece of the puzzle and just trusting that everything else will click into place. It's an all or nothing approach.
It really is.
Which brings us to that core idea. If you're going to replace the foundation of physics, what is that fundamental shift?
The shift is. It's radical. It's the replacement of the zero-dimensional point particle. In the standard model, everything, quarks, electrons, photons, they're all treated as these infinitesimal dots. No size, no internal structure.
Just mathematical points moving through space.
Correct. String theory says no. It replaces those zero-dimensional points with one-dimensional objects, tiny little filaments of energy, strings. These are the real fundamental building blocks.
And we have to talk about the scale, because it's so hard to wrap your head around. These strings are supposed to be the size of the Planck length, that 10 to the minus 35 meters.
The analogy really helps. If you blew up an atom to be the size of our entire solar system, a single string would be about the size of a tree on Earth.
Wow. Okay.
That's how much smaller a string is than an atom. And that extreme smallness is why we've never seen them. To all of our experiments, they just look like the points we've always assumed they were.
So the core idea is set. Everything is made of these ridiculously tiny, vibrating threads. But how do you get all the complexity we see in the universe? We have dozens of particles with completely different properties.
And that is the absolute genius of the theory. It's where the whole music of the cosmos idea comes from. The identity of any given particle is just the specific way its string is vibrating.
So it's like the entire universe is built on one kind of guitar string.
That's a perfect analogy. Imagine a violin string. You pluck it one way, you get one note. You press down on it, you get a different higher note.
A different frequency.
A different frequency. In string theory, an electron is just a string vibrating one particular way. A photon is the exact same kind of string, just vibrating in a different way. The strings are the single ingredient. The vibration is what creates the diversity.
So the whole zoo of particles in the standard model, all their different masses, their charges, their spins, are just different harmonic frequencies of the same fundamental object. That's a huge simplification.
It's a massive simplification of what reality is made of. It takes this collection of dozens of different fundamental particles and says, no, it's all one thing. All of matter, all of the forces are just the music being played by these threads across space-time.
And you mentioned that these strings come in two basic forms, which is important for understanding the forces.
That's right. You have open strings, which have two endpoints, and you have closed strings, which form a continuous loop.
Okay.
And this distinction maps pretty neatly onto the particles we know. Open strings are generally associated with mattoparticles like quarks and electrons and some of the force carriers that are kind of stuck to our world. But the closed strings, that's where the key to everything lies.
And looking at those closed strings is where we find this unexpected triumph of the theory.
The biggest one.
Here's where it gets really interesting, because I think the most compelling argument that string theory is on the right track, even without direct evidence, is that the math didn't just allow for quantum gravity.
It demanded it.
It demanded it. It solved the problem almost by accident.
It was an incredible discovery. The theory was originally developed to try and describe the strong nuclear force, but the mathematics kept spitting out this extra unwanted particle.
An error in the calculation.
Exactly. But when physicists actually looked at the properties of this unwanted particle, they realized it perfectly matched the checklist for the theoretical quantum carrier of gravity, the graviton.
Okay, before we go on, let's nail down that physics. What exactly does a theory of quantum gravity need? We know the particle has to be massless because gravity has infinite range, like light.
Correct.
But why the specific property of spin 2? What does that even mean?
That property, spin 2, comes directly from what's sourcing the force. In physics, the spin of a force-carrying particle is tied to the mathematical structure of its source. So for electromagnetism, the source is charge and current. Mathematically, that's a vector, or a first-order tensor. And that structure requires a spin 1 particle, which is the photon.
So spin 1 comes from a first-order source.
Precisely. Now, gravity is way more complex. Its source is something called the stress-energy tensor. This doesn't just describe where mass is, but also momentum, pressure, stress. It's a whole map of energy and matter.
A much more complicated object.
A much more complicated object. Mathematically, it's a second-order tensor. And the rules of quantum field theory are rigid on this. Any force particle sourced by a second-order tensor must be a spin 2 boson.
So if it were anything else, spin 1 or spin 0, it just wouldn't look like gravity at large scales.
It would completely fail. So the requirements are set in stone, massless and spin 2. And here is what's been called the mathematical miracle.
Yeah.
When you analyze the vibrational modes of a closed string, one of those loops, the equations mandatorily include a state in its lowest energy mode that has those exact properties.
Yeah.
Massless and spin 2.
Wait, so the math of a vibrating loop, it doesn't just allow for the graviton, it forces it to exist.
It's an obligatory, non-negotiable, low-energy vibration of the closed string. And that is the profound difference. QFT tries to shove gravity in by hand and gets infinities. String theory changes the foundation from points to strings, and the infinities vanish and the graviton appears, as a consequence of the theory being consistent with itself.
That self-consistency is what gives it so much power. It's suggesting that if the universe is built on strings, then quantum gravity isn't an add-on, it's a feature that has to be there.
And this detail about the closed string is also critical, because it's a closed loop. It isn't anchored anywhere, it's free, which, as we'll see, is what allows it to do things that other particles can't.
Right.
But This incredible breakthrough, the accidental discovery of the graviton, it came with a cost, or maybe a better word is a geometric imperative. For the theory to be mathematically consistent, to cancel out certain instabilities called quantum anomalies, it requires a space-time that's much bigger than what we see.
And this is the extra dimensions part. This is where a lot of people, they check out. Because our reality seems so stubbornly four-dimensional. 3 of space, 1 of time.
It certainly does.
So how many dimensions did the math first demand?
The very first version, which is called bosonic string theory, only described force particles. That one needed 26 space-time dimensions.
26. Okay, that's a bit much.
Clearly not our universe. To include matter particles, physicists had to introduce a new concept called supersymmetry. That gave us superstring theory, and that version requires 10 space-time dimensions. 9 of space, 1 of time.
And then even later, it turned out that all the different versions of the 10-dimensional theory were just aspects of a single, even deeper 11-dimensional theory called M theory.
Exactly. M theory is now seen as the parent theory. But the point is, whether it's 10 or 11, we're left with 6 or 7 extra spatial dimensions that we need to account for.
Where are they? I mean, we're definitely not bumping into a 5th dimension on our way to the kitchen.
They're hidden. The theory proposes they're hidden through a process called compactification. The idea is that these extra dimensions are curled up on themselves at an unimaginably tiny scale.
At the Planck lengths again?
At the Planck length.
So let's use that classic analogy, the ant on the rope, but maybe we can get a bit more technical with it.
A great analogy. Imagine a long, thin garden hose. From far away, it just looks like a one-dimensional line.
That's our macroscopic reality.
That's our 4D reality. But if you're a tiny ant walking on that hose, you see something else. You can walk forwards and backwards along the length, but you can also walk around the small circular part, the circumference.
That's the hidden compactified dimension.
Exactly.
So what's actually stopping us from seeing them? Is it just that we don't have enough energy to probe that small, or is there a fundamental reason we can't move in those directions?
It's mostly the geometry and the energy.
Yeah.
Because the dimensions are curled back on themselves, any movement along them is a tiny, tiny loop. You move an infinitesimal distance, and you're right back where you started.
I see.
Any energy needed to sort of unfurl that dimension is it's colossal, far beyond anything we can generate. Our entire universe of particles is, in a sense, too big and low energy to fit into those tiny pathways.
And this idea of hidden dimensions, it brings us right back to that huge mystery in physics, the hierarchy problem. The fact that gravity is so bizarrely weak.
It provides one of the most elegant potential solutions through what are called brane world models.
Brane, as in membrane.
Exactly. The idea is that our entire four-dimensional universe, all the particles we're made of, the photons, everything built from open strings, is confined to a membrane or a brane that's floating in a larger 10 or 11-dimensional space.
So we're literally stuck on this brane.
You're stuck on the brane. The open strings, because they have endpoints, are tethered to it. They can't leave. But the graviton,
The closed loop.
it has no endpoints, it's not tethered, so it's free to propagate or leak out into the full 10-dimensional space, which we call the bulk.
So gravity's influence gets spread out over all those extra dimensions.
It gets diluted. And because its strength is spread across a much larger volume, it appears astronomically weaker to us who are stuck here on our little 4D brane. Meanwhile, a force like electromagnetism is stuck on the brane with us, so it seems much stronger.
That's a really powerful connection, explaining a giant cosmic mystery with a tiny feature of a string.
It's one of the most compelling aspects of the entire framework.
So now we're at what is, for me, the most profound part of all this. We've got these 6 curled up hidden dimensions. And the truly mind-bending insight is that the specific geometry of those hidden dimensions dictates every single physical law we see.
That is geometric determinism. It's the central, beautiful idea of string theory. The geometry of that tiny curled-up space is the blueprint. It's the source code for reality itself.
So the shape determines a particle's mass, its charge, the strength of a force. What are these complex shapes even called?
They're known as Calabi-Yau manifolds. They are incredibly intricate, 6-dimensional mathematical spaces, and they have to satisfy very, very strict conditions to make sure the underlying string theory math remains consistent.
And their geometry is defined by things like the number of holes they have?
Exactly. Topological features like the number of holes or handles, their specific curvature, and even how you can wrap magnetic fields or fluxes through those holes.
So if the strings are vibrating through all 10 dimensions at once, the 6 small ones and our 4 big ones. How does the shape of the Calabi-Yau manifold actually constrain the physics we see?
Because the strings vibrate in that entire 10D space, their vibrations are limited by the shape of the space they inhabit. Think of it like sound waves in a really complex cathedral. The cathedral's shape, the number of domes, the arches, the corridors, it determines which musical notes can resonate and which ones just die out immediately. The Calabi-Yau shape does the same thing to the strings. It directly restricts which vibrational patterns can exist in our 4 large dimensions.
So if you change the geometry, you change the available notes. You literally change the available particles and forces.
You change reality.
Can we get specific? Is there a direct link between a geometric feature and something we can actually measure?
Oh, absolutely. This is what theorists have worked on for decades. They found, for instance, that the number of holes in the Calabi-Yau manifold seems to directly determine the number of generations of matter particles.
We have 3 of those, the electron, the muon, and the tau, and their quarks and neutrinos.
Exactly, 3 generations. And it turns out that a Calabi-Yau manifold with 3 of these relevant topological holes would mathematically produce exactly 3 generations of particles.
That is the ultimate promise of a theory of everything. All those seemingly random numbers in the standard model particle masses, force, strengths, they stop being arbitrary inputs and they become necessary consequences of hidden geometry.
You replace arbitrary constants with inevitable geometric features. And this elegance, this promise, it fueled decades of optimism. The hope was that we would find one single unique Calabi-Yau shape that produced our exact universe.
But that's not what happened.
That is not what happened. And this led directly into string theory's deepest and most difficult modern crisis.
A landscape problem.
Landscape problem. The constraints on the geometry are very strict, yes, but they're not unique. It turns out the rules still allow for a truly enormous number of different, consistent geometric shapes.
How is that possible if the rules are so strict?
It's because it's not just about the shapes. It's about all the ways you can wrap those internal magnetic and electric fields, the fluxes through all the different holes and cycles in the manifold. It's a combinatorial explosion.
So for every shape, there's a huge number of ways to arrange the fields inside it.
Exactly. And each one of those choices stabilizes the geometry into a specific consistent energy state or a vacuum. And each vacuum represents a completely viable, mathematically self-consistent universe with its own set of rules.
And the number of these possible universes is famously huge.
The number that gets cited most often is around 10 to the 500.
Let's just pause on that number, 10 with 500 zeros after it.
Yeah.
It's a number so large, it's meaningless. It's far, far larger than the number of atoms in our entire observable universe.
It is.
And this just crushes that original dream of a single unique theory of everything. So what does it mean? Is it a flaw in the theory, or is this just what reality looks like?
That is the single question that defines the theoretical physics community today. Critics say, look, if your theory allows for 10 to the 500 solutions, it hasn't predicted our universe. It's just given a catalog of every universe that could possibly exist.
It's no longer a predictive theory.
It transforms from a unique toe into a theory of everything that can mathematically exist. But string theorists would argue this isn't a bug, it's a necessary feature. They would say that any truly unified quantum mechanical theory of gravity has to describe the entire space of possibilities. The challenge just shifts. It's no longer about finding the one equation. It's about figuring out why we live in this particular one out of the 10 to the 500 possibilities.
And that brings us right into the biggest debate about string theory today, testability. I mean, if the strings are too small to see and the theory gives you a near infinite number of outcomes, how can you ever prove it right or wrong?
That is the core of the criticism, and it's a very serious one. For a theory to be scientific, it has to make unique predictions you can go out and test, or, just as importantly, predictions that can be proven false.
Right, falsifiability.
And as we said, the strings exist at 10 to the minus 35 meters. The Large Hadron Collider, our most powerful machine, only gets us down to about 10 to the minus 19 meters. There's a colossal gap.
And the flexibility from the landscape just makes it worse. Critics say it feels like you can always find some incredibly complicated Calabi-Yau shape in that list of 10 to the 500 that happens to match the physics we already know. It looks more like retrofitting than prediction.
It can. And that leads directly to the very controversial method that theorists use to navigate this landscape,
Yeah.
the anthropic principle.
Which feels like you're giving up on physics and just turning to statistics. Aren't we just saying, well, we're here because we're here?
It is deeply unsatisfying for anyone who wanted that unique, elegant solution. But if the landscape is real, it might be a statistical necessity. The anthropic principle is an attempt to solve the fine-tuning problem.
The fact that our universe's constants seem perfectly exquisitely dialed in to allow for life to exist.
Exactly. If the strong nuclear force were just a couple of % weaker, the only element in the universe would be hydrogen. No stars, no planets, no people.
And the anthropic principle says, what?
It says that out of those 10 to the 500 possible universes, only a vanishingly small fraction of them have the right physical constants for complex structures and conscious observers to ever evolve. So we find ourselves in a universe that supports life simply because we couldn't exist anywhere else to make the observation.
It changes the question from why are the laws this way to what conditions are necessary for us to be here to ask the question.
It does, and that is the philosophical price of the theory. You sacrifice Einstein's dream of a single solution for the statistical reality of a multiverse.
So if direct testing is out for now, and the anthropic principle is more of a philosophical argument, what are the actual concrete ways we might find some indirect evidence?
The biggest experimental hope for decades has been the search for supersymmetry, or SUSY, the superscale superstring theory.
And why is SUSY so critical for the theory to even work?
It's a requirement for mathematical consistency. Without it, the theory has all sorts of problems, and most importantly, it can't properly include the matter particles, the fermions, that we're made of.
So what does it actually predict?
It predicts that every particle we know has a much heavier superpartner. So for every fermion, like an electron, there should be a corresponding boson, which we call a selectron. And for every boson, like a photon, there should be a heavier fermion partner, the photino.
So finding even one of these particles at the LHC would be huge. It wouldn't prove strings exist, but it would be massive support for the underlying framework.
It would be the biggest discovery in particle physics in 50 years. But the LHC hasn't found any of them, at least not at the energy scales we've been able to search so far.
Which puts more pressure on the model.
It does. It forces theorists to push these superpartners to even higher, less testable energy ranges. But even with all these challenges, the mathematical rigor of the theory has produced incredible results in other areas.
Right, it's been useful even if it isn't the final answer.
Absolutely. The math has led to huge advances in pure mathematics itself. And for physics, it gave us an indispensable tool called the AD-SCFT correspondence.
Can you just quickly define what that is?
It's a fascinating duality. It shows that a theory of quantum gravity happening in a specific kind of curved space-time is mathematically identical, equivalent to a normal quantum field theory living on the boundary of that space-time in one less dimension.
So it connects a gravity theory to a quantum theory. That's a working model of quantum gravity, even if it's not in our exact universe.
It's a theoretical laboratory for black holes. It's the only framework we have that has successfully, from first principles, calculated the quantum properties of a black hole and confirmed Stephen Hawking's earlier results. It suggests that even if the TOE is elusive, the string framework contains incredibly deep truths about how space-time and quantum mechanics really fit together.
So we've gone from these tiny point particles to vibrating strings, and we saw quantum gravity just pop out of the math as an unavoidable consequence. And then we realized that all of reality might be defined by 6 hidden dimensions curled up into these incredibly complex shapes.
The Calabi-Yau manifolds.
String theory gave us that quantum gravity framework we were looking for, but the cost was this colossal landscape of 10 to the 500 possible universes.
Its strength is still that it unifies everything into one single element, the string, and it includes quantum gravity naturally. Its weakness is the sheer number of choices the landscape presents, which forces us to fall back on things like the anthropic principle.
And at the end of the day, the message seems to be that geometry is destiny. The exact fixed shape of those hidden dimensions determines every number we measure in our universe.
Which leaves us with a final, really provocative thought to consider.
Okay.
If all the laws of our universe are just dictated by one specific stable geometry out of that vast landscape, what if that geometry isn't perfectly static? What if the universe isn't completely stuck in its current energy state?
You mean, what if the shape of those 6 hidden dimensions is actually dynamic, like it's slowly changing over cosmic time?
Precisely. If the Cavia manifold were to slowly morph or breathe, even slightly, those changes in geometry would alter the allowed vibrational patterns of the strings. The music of the cosmos, the fundamental constants of our reality, would subtly change over billions of years.
So what we call fundamental constants might not be constant at all.
To us, as observers trapped in our four dimensions, it would look like things like the fine structure constant or the ratio of an electron's mass to a proton's mass were marginally different in the distant past than they are today. It suggests the equation we're looking for might not describe a static, eternal reality, but an ever-shifting symphony.
An evolution of the laws themselves, written in invisible geometry. Wow. That is a fantastic thought to end on. It suggests our work might just be starting. Thank you for guiding us through this incredibly deep dive into the music of the cosmos.